The next two videos will be on section 2.3 in our text about the prime numbers. First of all, we want to define a prime number, and we want to see how the prime numbers, or why the prime numbers, are called the building blocks of all natural numbers. So let's review the notation for the natural numbers. We use capital N, and using set brackets, it's the set of numbers containing 1, 2, 3, all of the numbers that we count with. Don't forget to put the dot, dot, dot. What is a prime number? Well, we'll define very carefully a prime number, and you should know all parts of the definition. So a prime number, I'll just use this for number, is a natural number. A natural number greater than 1. 1 is not a prime number. Greater than 1 that is divisible by only 1 and itself. So the word natural number is important. A prime can't be a number like 2.6. It's greater than 1. That tells you that 1 is not a prime. Later we'll see why we don't want to include 1 as a prime number. And it is divisible by only 1 and itself. So there the important word is only. So what are the prime factors of 15? Well, we have to know exactly what factor means. A factor is, well, a factor of 15. A factor of 15 is a number that divides 15, divides 15 evenly. A factor is part of a product. So we could say 1 and 15 are factors. 1 and 15 are factors. Because, I'll put just BC, because 1 times 15 is equal to 15. They each divide 15, but they're not prime factors. The numbers that are prime factors are, of course, and I know you know this, 3 and 5 are prime factors because they are prime numbers and they divide 15. In fact, 15 is equal to 3 times 5, so we could say that 3 times 5 is the prime factorization of the number 15. The prime factorization theorem is very important. I know that you use this in high school a lot. Every natural number greater than 1 is either a prime number or it can be expressed as a product of prime numbers. When you express it as a product of prime numbers, for example, 8 is equal to 2 cubed, 2 times 2 times 2, or we already said 15 is equal to 3 times 5, or 3 times 5, or 10 is equal to 2 times 5. These are called prime factorizations. Prime factorizations. And lots of times in high school, I know that you had to prime factor numbers. That means to find their prime factorization, or to write them as a product of prime numbers. And something we will not prove in our class, but if you like mathematics, you could definitely understand the proof. If you wanted to look it up and hand it in to me, I would love to discuss it with you and probably give you some extra credit. Prime factorizations are unique. We're not going to prove this in class, but I want you to know it. It's very important. The prime factorization of a number is unique. For example, 8 is equal to 2 times 2 times 2. We cannot write it as any other product of prime numbers, simply 3 factors of 2. So every natural number greater than 1 that is not prime can be written in one and only one way, uniquely, as a product of prime numbers. Now, to decide if a large number is prime can be difficult, if not impossible. But of course, numbers with 4 digits, we can tell if those are prime by just trying to divide them by primes. So if we take this example, 1193, we would just start dividing it by prime numbers. And let's see, let's go ahead and start. Let me write down the first few prime numbers. You want to always do that. We have 2 as a prime number, and then 3, 5. I know that you all know these. 7, 11, 13, and then 17, and then 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and so on. So these are all prime numbers. And we want to try dividing 1193 by these primes. Well, 1193 is not even, so we know it's not divisible by 2. How about 3? Well, you could take your calculator and try to divide the number by 3, and you will see that it is not divisible by 3. It doesn't end in 0 or 5, so it's not divisible by 5. Take your calculator, try to divide it by 7, it's not. Try to divide it by 11, it's not. Well, now the question arises after you've tried this a few times is, how many primes do we have to try? There's a whole lot of primes up to 1193. Do we have to try dividing it by all of those? And of course, we do not. The interesting thing is, or the handy thing, is that if you take the square root of the number, the square root of 1193, plug it into your calculator, you'll get the square root is about 34.5. And it turns out that we only need to try primes that are less than or equal to this number, the square root. So we need to try dividing, I'll just use shorthand, dividing by the primes which are less than or equal to the square root of the number. Well, that means we need to then try dividing by 13, 17, 19, 23, 29, and there's one more prime we'll need to try, 31, and that's it. So to tell if 1193 is a prime, we still need to try dividing by these numbers. And I'll leave it to you. You try those in your calculator, and you'll find no, 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 no. So since 1193 is not divisible by any prime less than or equal to its square root, we know that we can conclude, by the way, 3 dots in the corners of a triangle means therefore. Therefore, Therefore, 1193 is prime. It's a prime number. It has no divisors other than 1 and itself. So what I want you to get from this slide is that to see if a number is prime, you just try dividing it by a few primes. But if you don't immediately get a divisor, take its square root, and you'll see how many primes you have to try before you are sure. This is just for you to see why that is true. I'm not going to ask you to repeat this, but just see why, because when you understand why something is true, you tend to remember it. Take the number 144. I chose that because it's a perfect square. And I wrote down all the different ways to factor 144 into 2 factors. So you could write it as 2 times 72, 3 times 48, etc. And we get down to 12 times 12. Notice I'm just increasing the divisors here. 2, 3, 4, 6, 8, 12. And then the next divisor is 18. And that's 18 times 8. Oh, well, we already had 8 times 18. Then you have the divisor 24, but we already had 6 times 24, and so on. So you see that once you get to its square root, the other factors beyond that are just repeats of factorizations you've already checked. So you only have to check a number to its square root. I hope you can see why we don't get new factors after we pass the square root of the number. This is something else that will just interest you. I just made up that number, of course, by just pressing any numbers. And what you have there is about 250 digit number. So this is a huge number, and we wouldn't know how to say the number, and we really couldn't make any sense out of it. We don't know anything that's that big, but certainly it is a number. And it has a unique prime factorization. We know that can be proven. But we can't prime factor that number. It's impossible. If you put, in fact, our authors mention in the textbook, if you take a number this big and put the fastest computer in the world on it, trying to pick primes to divide it by, it would take centuries for it to ever figure out a prime factorization, if ever. So some numbers are so large you cannot prime factor them. You know that there are primes that divide it. You know it has a prime factorization, a unique one, but it's impossible to find. And if this interests you, you could read section 2.5 in our text. It's called Public Secret Codes and How to Become a Spy. Our inability to factor numbers this big is the key to devising codes to send private information on the web. So again, section 2.5, we're not going to study this in class, but the fact that we can't prime factor numbers this big is the key to making codes, let's say, codes for sending private information on the web, and even private information during war and things like that, private between countries, and it's there's many uses for it. the National Security Agency uses these techniques to code secret information. And you can read about that in section 2.5. Now, these divisibility rules are not in the text, but they're really handy for doing some of the problems that you'll be doing in class and in preparation for the test. So let's just review them. I know that you know the divisibility rule by 2. If a number is even, in other words, if it ends in the digit 0, 2, 4, 6, or 8, it's divisible by 2. And the divisibility rule for 5, I don't think we need to write down. If a number ends, if its last digit furthest to the right is 5 or 0, then it is divisible by 5. And by the way, I keep using the word digit, and I've been meaning to tell you exactly what it means. It's an important word. Let me just mention it now. Digit. The digits are just the characters that we use to write numbers with. 0, 1, 2, 3, 4, 5, 6, 7, and this digit right here, and the one that looks like that. Those are digits. They're like characters. They're like saying A, B, C, D. Those are letters with which we write our language. Those are the characters with which we write our numbers. So when you refer, I've noticed on some of your in-class work, you'll write a number like 123.0126, and you'll say, you'll refer to these things as numbers. Those are just the digits of the number. So call them digits, and we won't get mixed up with what you're talking about. When you're just using those characters, they're not numbers. They're just the way that we write the number. All right, so, all right, we want the divisibility rule for 3. So a natural number is divisible by 3 if the sum of its digits. And now you're looking at the sum of the digits. That sum you're looking at as a number is divisible by 3. So you might say, well, it's easier just to use my calculator, but what if I gave you a number like this? Let's say I gave you a number 1000112000113. Let's see, 1, 2, 3. What if I gave you that? You might not want, your calculator might not even take that big of a number. So you can quickly decide if it's divisible by 3. Sometimes this divisibility rule is handy. Just go across and add up the digits. 1 plus 1 plus 1 is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The sum of the digits is 12. 12 is divisible by 3, and so is the number. So this is a handy, you're going to need this in doing your problems. And then the other rule that is very handy is 11. A natural number, a natural number is divisible by 11 if the alternating sum of its digits is divisible by 11. Okay, well, first of all, what do we mean by an alternating sum? I think an example is the best way to show you. If I take a really big number, like let's take one that you couldn't just stick into your calculator. 1, 2, 3, 2, 7, 6, 1, 2, 0, 0, 0, 0, 0, 0, 0, 3, 4, let's say. Okay, it's a great big number. Is it divisible by 11? Well, we're going to look at the alternating sum of its digits. So we start with just taking the first digit, 1 minus 2 plus 3 minus 2 plus 7 minus 6 plus 1 minus 2. And now these zeros aren't going to add or subtract anything, so I just have to keep track here. Minus 2, and then I'll have a plus, minus, plus, minus, plus, minus, plus. So then I have minus 3 plus 4. Notice I didn't want to write all those zeros down. So when I got to minus 2, I knew it would be plus 0, minus 0, plus 0, minus 0, plus 0, minus 0, plus 0, minus 3, plus 4. Okay, and if you add all this up, well, we get negative 1 plus 3 is 2, minus 2 is 0, plus 7 minus 6, we have 1, plus 1 is 2, minus 2 is 0. Minus 3 is minus 3, plus 4 is 1. I didn't mean for it to turn out to be 1. Let me check that. I'm going to put it on pause and check it so you don't have to. Well, I did add up the alternating sum correctly, and we would get that this number is not divisible by 11 because the alternating sum of its digits is 1, and 1 is not divisible by 11. But now I'm going to do something, I hope it doesn't confuse you. I'm going to pretend that I had written a 3 here instead. And then I would have plus 3 here, and I would have gotten 0. And 0 is divisible. I just wanted to make this point to you. 0 is divisible by 11. So this number here, if it had a 3 at the end instead of a 3, 4, so this number here is divisible by 11. And I just wanted to mention this because students come out with this all the time and they think that 0 is not divisible by other numbers. And 0 is divisible by all numbers. 0 over 11 is equal to 0 because 0 times 11 is equal to 0. You can't divide by 0, but 0 is divisible by 11 or any other natural number you choose except for 0. You can't divide anything by 0. Okay, some of you can just fast forward to this if you remember how to prime factor. But I figured some of you might need review, and this is something you need to know in this section and know for the test. So let's prime factor this number, 1,386. I'm just going to do it the way I've seen students do it in class. I think this is probably the way you learned it. We can see right away that this is an even number divisible by 2. I usually start with the smallest prime factors and just go up from there. And divide and you'll get 693. Well, now the sum of those digits is divisible by 3, clearly. So this number I know is no longer divisible by 2. I don't have another factor of 2 in there because 693 is not even. But I can divide it by 3 and just use your calculator. You get 231. Now look, this one still is divisible by 3 because 2 plus 3 plus 1 is 6, which is divisible by 3. So we'll put 3 in again, dividing using your calculator. You get 77, which is 7 times 11. So the prime factorization you write this way. You see the prime factors are here. Don't just leave it like this. The prime factorization is written this way. 2 times 3 times 3 is 3 squared times 7 times 11. This is the prime factorization, and that's the way you write it. All right, the next example, 3,289. Well, let's take it up here. 3,289. Let's see, what would it be divisible by? So let's just start out with some prime numbers and cross them off. We know it's not divisible by 2. It's not even. let's see, 3. The sum of its digits is 6, and 6 is 12, 13, 14, plus 19 is 23. No, it's not divisible by 3. Or you could just be using your calculator. If you come out with a decimal number, you know it didn't go in evenly. 5, no, it's not divisible by 5. It doesn't end in 0 or 5. 7, try it with your calculator. It doesn't work. Hopefully you put these on pause and try these yourselves. The next prime after 7 is 11, and sure enough, you try it and it does divide, and so we can write this is equal to, using your calculator, 11 times 283. Okay, and so now we have to keep trying to factor this number. You would try 11 again. You do not go back and have to try 2, 3, 5, or 7, because if 2, 3, 5, and 7 did not divide 3,289, it's certainly not going to divide any of its factors. But we would try 11 again. The alternating sum, oh, by the way, the alternating sum up here was 0, which is divisible by 11. Here, the alternating sum, 2 minus 8, would be negative 6 plus 3 is negative 3. Nope, not divisible by 11. So you might try, we're done with 11, you might try 13, and it won't go in. And so now you're thinking, well, maybe 283 is a prime. Well, how do I check? How far do I need to go? Take the square root of 283 using your calculator, and it is approximately 16.8. So after 13, the next prime is bigger than that. We're done. All you have to do is try the primes up to the square root of 283. We had already tried 2, 3, 5, 7. Tried 11, it didn't work. 13, no. So 3,289 is prime factored 11 times 283. 283 is a prime. So see how that square root can help you make this process shorter. This is a problem that you will see one similar to it on the test. This is a sequence. In other words, an infinite list of numbers. A sequence is an infinite list of numbers. And we see the first one has 4 ones for digits, and the second one has 5 digits, all ones, 6 digits, all ones, etc. Are all of these numbers prime? Well, if you're asked a question like this, you can almost for sure know, well, you can know, unless it's the sequence of prime numbers, that these are not all prime. And in fact, look at the very first number. The answer to the first question, no. In fact, just the very first number, 1, 1, 1, 1, is divisible by 11. Divided by 11 is equal to 101. You could see right away the alternating sum of the digits here is 0. So it's divisible by 11. They are not all prime. Now the next question says, if not, can you describe infinitely many of these numbers that are definitely not prime? Well, let's see. There's 2 ways that you could answer this question. I'm going to change colors. 2 ways. One, you could consider the alternating sum of the digits. The alternating sum of the digits was 0 here. Why? Well, because there was an even number of ones. So the alternating sum of the second number's digits would be 1 minus 1 plus 1 minus 1. 1. It would be 1. That's not divisible by 11, but the third number has an even number of ones, and so the alternating sum will again be 0. And we can see that, let's see, how could I write this the best way? The alternating sum of digits is 0 for every number with an even number of digits. The digits are all 1. So every other number is divisible by 11. And that's infinitely many. Every other number is divisible by 11. But we could also look at this another way. There's another, let me go up here, another way to look at it, and I'll change colors here. Another way to see it is that this one that has 1, 2, 3, 4, 5, 6, the sum of the digits is 6. If I put in 9 ones, the sum of the digits is 9. So we could say that every third number in the sequence, has a sum of digits divisible by 3. So we could, we know that every third number in this sequence is divisible by 3. So there's another infinite number of these numbers that are divisible by 3. So the last question we'll ask is, how many primes are there? How many do you think there are? I think most of you would think correctly that there are infinitely many. Now learn how to use these words. There are infinitely many primes. But how do we know that? We just said a few slides back that if a number is too big, it's absolutely impossible to prime factor it. So how do we know there's infinitely many primes? And what we're going to do in the second video is to prove this. It'll be the first example of mathematical proof. And it's amazingly beautiful and quite simple as to how we can prove without a doubt that there are infinitely many primes. Even though that number we looked at with 250 digits, we don't know if it's a prime or not, but we know that there are primes bigger than that number, bigger than any number. So we'll prove that next time.